All right, so we're going to be talking a bit about orbitals today. And so specifically molecular orbital theory and how that relates to chemical reactions. So we kind of have hinted at this before, but we haven't actually gotten a nice
Thank you.
a nice solid foundation where we're looking at it all the time, right? So if you remember chapter 6 and 7, we went ahead and have introduced the most common elementary steps. These are the steps that will combine to form pretty much all the organic chemistry reactions that you would want to do, unless you go off into more advanced chemistry at some point. This would be all the chemistry reactions that would even do things like make most of the drugs that are out there, that sort of thing, okay? Actually, you gotta get pretty complicated to get out of these elementary reactions. So, we've actually covered a lot of ground. So, one of the things you've noticed is that we've been using these curved arrows to depict those changes in valence electrons. We've described the flow of electrons from electron-rich to electron-poor sites. We focused on the Lewis structure models to explain those changes, but those Lewis structure models don't really talk about the orbitals at all, do they? Okay? In fact, they kind of are orbital almost independent, aren't they? The orbitals are actually more introduced in the VSEPR. Remember the VSEPR? Valence shell repulsion? Okay. So, again, we don't really understand so far what's going on with the orbitals. Why are these reactions happening? Okay? We've described it as electron-rich, electron-poor. The frontier molecular orbital theory, FMO, is going to be what accounts for that flow of the electrons in these elementary steps and why things have to be aligned correctly for them to react. Why are this lone pair combining with that? Why are these things happening? Okay. It is actually exactly like it says. So if you break down that frontier, what does frontier normally mean? Yeah, the outermost fringes, right? When we're talking about molecular orbitals, we have a place where we have a boundary, a frontier, that is between the highest energy occupied molecular orbital, right, and the lowest unoccupied molecular orbital. Do you remember what those are called? HOMO and LUMO. And that's where our frontier is, isn't it? We have the lowest energy unoccupied. If you're going to get electrons going somewhere, that's going to be where they're going, right? And then you have the highest occupied. If you're going to pull electrons from somewhere, it's going to be the high energy occupied one, right? Okay. And so it actually makes really nice sense once you start thinking about it in these terms. Okay. This also helps to justify those stereochemistries we're observing in these particular steps. Why do you have a stereochemistry that happens like this? Because you have to have an overlap of these orbitals, right? And the orbitals actually have directions they have to point in, don't they? And so there you go. Look at that. We're going to connect the fibers. We're going to connect so we understand. So right here we actually have a nice free energy diagram. And what we can see here is that, again, these would be the reactants, products here, right? And then we go over this energy barrier. What's that energy barrier? That's that activation energy, isn't it? So whenever we do reactions, we always have to do that. We always have to go from reactants, go over the energy barrier to products, right? And you can't have reaction without going over the energy barrier. Otherwise, you just go right back into reactants, don't you? Okay. All right, so now you can have an energy barrier where if we look at these reactions, these energy barriers may seem extremely high. And part of that is we're not looking at, so far, that overlap of orbitals. We're not looking at those differences between the lowest unoccupied and highest occupied molecular orbitals. Okay? So if you start looking at these feasibility of these elementary steps, you can actually start looking and seeing that these energy barriers will start coming down drastically just with small changes. Like, instead of trying to overlap like this with two orbitals, we overlap like that, right? And that's going to make that a lot more stable when they start trying to come together, isn't it? Okay. All right, so one of the main stabilizing contributions is going to involve the frontier molecular orbitals again, like we had discussed. The HOMO of one reactant and LUMO of the other reactant have to substantially have a net overlap in your transition state. Where's that transition state again? Yeah, that's that activation energy, right? This is the transition state here. It's the highest energy state you have to pass through, okay? And so when we're looking at these things, we're not changing reactants and products, are we? No, that's not gonna... It's gonna have whole new molecular orbitals that have nothing to do with the previous reactants in the products, right? Because we'll be breaking and making new bonds, okay? There'll be new molecules, right? And so what we're going to be looking at here is we're going to be looking at the activation energies. What is the activation energy? Is that thermodynamics? Is that whether the reaction happens at all? So the activation energy does correspond to if the reaction happens, but doesn't correspond to whether it's spontaneous, right? So spontaneous is going to be thermodynamics. It's going to be reactants versus products, right? We don't care about the pathway in between. This is going to be kinetics, the pathway between, okay? All right, so if there's literal or no overlap between the HOMO and LUMO orbitals, then the transition state tends to not be sufficiently stabilized. That means you'll have a very, very large activation energy, and we call this forbidden. But like forbidden things in society, does forbidden things in society mean they don't happen at all? No, in fact, the fact that they're forbidden tells you that they've probably happened, right? Yeah. And so, just like reactions, forbidden means that it's going to be very high energy. It's not likely to occur, but you can get edge cases where it would occur, okay? Now, in the reactions, these forbidden reactions, these forbidden overlaps, these forbidden ways forward, they are very unlikely in comparison, okay? Because you're talking about probability. Yeah. If there's a much faster pathway, they almost don't occur at all, okay? Okay, but I don't want forbidden to me, you get the wrong idea in your head. If you go off to grad schools, whatever you're going off to, that forbidden means it's impossible to ever happen, period. I never have to think about these things ever again. Okay. It happens. Okay. So this is actually looking at in terms of an energy diagram, right? Now, notice that if we try to match up a HOMO with a HOMO, what would happen? What is a HOMO again? Highest occupied molecular orbital, right? So if we try to match up two full HOMOs, do we have anywhere to put those electrons? No, we don't have anywhere to put them, right? And so you can't match up two HOMOs, can you? Because you have nowhere to put the electrons. Oh, by the way, can everybody get into my my YouTube videos? Okay, there's still... has anybody tried this weekend? Okay, please do try and let me know. My Gmail account that was hosting those has been flagged for spam. I've never sent a message from it. And so they denied my request to reactivate it. And I don't know. I think it's just the Gmail part that's not working now. But please let me know if the videos are accessible or not. Okay. Yeah, I've never, in my 20-something years of using Gmail, I've never had that happen. And I have no idea why the hell it's going on. So, anyways, it's accessible? Oh, good. Good. Because it's actually very difficult to download and re-upload off of YouTube. Okay. What if we match up two LUMOs? What would that do? Yeah, they're both unoccupied, right? Yeah. And so if you match up two LUMOs, you have no electrons to move into the other orbital, right? Okay. Could you theoretically match up two HOMOs? Yeah, you'd have to have each one with only one electron, right? That could theoretically line up. Okay. And you can actually match up a HOMO and a LUMO with only one electron. That has been confirmed in the case of carbon. That's now science. It's not in any books because it only just got discovered and confirmed like a couple weeks ago. But yeah, pretty cool, huh? All right. This right here would be what the reaction would then look like. You take the HOMO and LUMO of the two reactants. They would then make a transition state. That transition state's going to be higher energy overall, right? And you would have this offset. You'd have the transition state low energy orbital where it would be a matchup, right? And then you'd have a anti-bonding one that would get generated. And that would be where you would have it, remember the anti-bonding where it's on both sides and it wouldn't be a good overlap and the electrons would pull the things apart? That'd be that. Okay? And in the case of two HOMOs, this would actually fill both sides, wouldn't it? And that's why no bond happens. In the case of two LUMOs, nothing would get filled, and so there's no overall energy savings, is there? Okay. All right, so the species that contributes the pertinent HOMO and in the FMO interaction is going to be your relatively electron-rich species. This is going to be the Lewis base. This is going to be your nucleophile. This is going to be the ones donating the electron density, right? In the case of the species that contributes the LUMO, this is going to be the relatively electron-poor. It's going to be your Lewis acid. It's going to be the electrophile. It's the one that's taking electrons onto it, right? How do I predict which one's which? I'm looking for the overall lowest energy state. So the one that would give me the HOMO and LUMO that blend to give me the lowest energy state, that's the one. That's my reaction. That's the one that's donating the electrons. That's the one that's taking the electrons on, right? If we look here, if we tried to do, so we have this match. That's the one we actually are doing, right? If we look to this match, you see that this is a lot higher. And this is just a little bit lower. So overall, we would get a higher energy state. Okay? And that always has to be true if you're electron rich and you'd have a poor electronegativity to hold on to those, right? Then you're going to donate the electrons very easily, aren't you? And that means you're going to have a fairly high energy state that you can donate those electrons from. Okay. Now, some elementary steps are going to be the reverse of each other, but they're going to receive different names. So when we look at these FMO interactions, right? Everybody okay with FMO? Frontier molecular orbital interactions. Okay. There's not really that much of a difference between like a heterolysis, where we take the electrons from one, right? And we look at the opposite direction, that'd be a coordination, wouldn't it? So one heterolysis, we take the electrons onto one species, right? And the other one ends up not having the electrons. If we go the reverse, that's a coordination, isn't it? Only one species donates both electrons. Okay. These right here would be the opposite of each other as well. We have nucleophilic addition and nucleophilic elimination. Okay. Those are just the reverse of each other, right? When we're looking at energy diagrams, it doesn't really have a lot of meaning when we're looking at the energy diagram, does it? Yeah. Because it's like looking at a hill from the front and back. Is there that much meaning at looking at a hill from the front and back? Do you call the hill different names? No, no, you don't, do you? And so that's what we're seeing here. We're calling the hill different names because we looked at it from the perspective of the reactions, right? What we're getting out from the reactions. In this case, in FMO, it really doesn't have any meaning because we're going to be looking at the energy diagrams. The electrophilic addition, electrophilic elimination, these are actually reverses of each other as well. We would actually apply the FMO theory separately to each step. It's more convenient to take advantage of these ideas. If an elementary step is allowed in the forward direction, then we allow it in the reverse direction as well. Because if you can walk a pathway forward, you can always walk it reverse, right? And that has to be true in any energetic sense. Okay? Same thing as going up or down the stairs, right? If you can go down the stairs, you have to be able to go up them as well. If the elementary step is forbidden in the forward direction, then it will be forbidden in the reverse direction as well. And a kind of easy way to think about that is if it's forbidden in the forward direction, that meant that had too many electrons that I was trying to fill in. If it's forbidden in the reverse direction, that's still going to be true, isn't it? That we can't actually split those electrons that way because we have nowhere to put them, right? Okay, so let's try out a question. Everybody go ahead and register on. This will also make sure I have attendance, which is good. Okay. All right. Everybody join me in my quiz. Right. I'm going to go ahead and head to the question so you can start thinking about it. You can still join if you need. So, which MOs have to overlap for the reaction to occur? Go ahead and get that answered. Wow, I probably need to keep that door open. Almost looking forward to it getting cold. It's not always a dang stuffy, sweaty mess in here. All right. Okay, folks, I'm moving on, so make sure you get something in. Okay, and 94%, and that is correct. So for a reaction to go forward, you typically have to line up the HOMO and LUMO, right? Lowest unoccupied, highest occupied molecular orbitals. Okay, very good. I don't know why that's showing up, shouldn't it? Okay, so the principle of microscopic reversibility. This is going to be if the reaction is the reverse of another, it must follow the same path in the energy diagram and must proceed through the same transition state. This is, again, a theory. The FMO theory is also a theory, of course. So the FMO theory is going to focus, again, on the energy barrier. That's that of the elementary steps. Remember, the elementary steps are individual steps of these reactions, right? And that's primarily the kinetics. It's not going to be the thermodynamics. So this reaction is just going to tell you how fast something happens and how much energy it takes for it to initialize, okay? It's not going to tell you if the reaction is spontaneous, if it happens on its own power, right? That'd be thermodynamics. Okay, so let's go ahead and look at some of these elementary steps and discuss their frontier molecular orbitals. So right here we have HO. This is your Lewis base. It's reacting right here with the Lewis acid. Everybody okay with that so far? Okay. Now, which one has a HOMO and which one has a LUMO to contribute to this? Which one would you expect? Yeah, that's the one with the occupied molecular orbital that's going to overlap and contribute electrons, right? Very good, yeah. And that's the easy way to think of it all the time. Unoccupied means it's getting electrons on it, right? Yeah. And so you can use a very outcomes-based thought process for this. Okay, and so again, we're going to be donating electrons from our HOMO into the unoccupied LUMO. That overlap is going to be what causes a transition state. Now, in this reaction, we don't demonstrate any transition state, do we? But when these reactions occur, they actually have to have a state where the hydrogen, that's bonded to both the oxygen and the chloride, right? That has to exist. Just like when you hand something to somebody, at one point, it's in both people's hands, right? And has anybody ever noticed when you hand stuff to somebody, especially really light stuff that's not real heavy, there's this moment where, like, neither of you are sure of who's holding on to it, right? And sometimes you guys drop it. I mean, that's kind of what's going on here, right? At that transition state, they're both going to be holding on to it, and this could go in either direction, couldn't it? Okay. All right, so the HOMO and LUMO are going to have substantial net overlap. So again, this reaction right here, this is actually allowed. Can everybody see that HOMO and LUMO nicely overlapping? And so that electron density can get pulled onto that hydrogen, and that hydrogen can release the electron density here to the chloride, right? Okay. Everybody see that nicely? Fantastic. Great overlap, right? Okay. Okay. So what about this overlap? Is that electron density going to be able to flow into that orbital? No, that's a damn mess, isn't it? Yeah. So in this bond here, we already have electron density, don't we? So the electrons can't flow into those partial overlaps of those orbitals, can it? That's not going to be able to make a bond easily. We would have to have tremendous amounts of energy behind this to basically cause these electrons to get shunted out and then re-put back on, right? Okay. And so this right here is a forbidden FMO, right? A forbidden frontier orbital overlap. Okay. Okay, so let's look at the bimolecular nucleophilic substitution. This is the SN2 elementary step. Mm-hmm.
Was that last slide saying like it joins to both of them, so it doesn't bond to just the hydrogen?
No, this last slide is saying that this is a forbidden overlap. We don't have a reaction. Yeah.
How is it different from the... I mean,
so in this one right here, this hydrogen, this is the part of the hydrogen orbital that doesn't have any electrons in it. Yeah. So what's happening is these are overlapping, and because that's the unoccupied, the highest energy unoccupied over here, and the lowest, the highest energy occupied, lowest energy unoccupied, orbitals overlapping. Here, we can have the electrons flow onto that hydrogen and start making a bond. Okay. In this case here, this is the forbidden overlap. This isn't overlapping with any orbital. There's no molecular orbital this actually has a good overlap with. It kind of has a little here and a little here, right? But our problem is, in both of those cases, that's actually space that these electrons in the bond here are occupying. So we would have to displace those electrons somehow. And that's extremely high energy. And so what's going to happen is, under normal conditions, these are going to come near each other, and then the electrons are going to repel each other, and they'll just fly off. And you'll get no reaction for the collision. Okay? Do you guys remember where you did the activation energies and you calculated those with the Arrhenius number? That meaningful collisions number? This is actually the meaningful collisions number.
So that's like they hit each other the wrong way.
Mm-hmm.
Nothing happens.
Yep. It'd be like me trying to grasp my hands, but I went like this instead. I don't really get a grasp, do I? No. Now, the funny part is if it did the reverse, it would be like me doing my backhand, right? And you'd really have some troubles because there's a lot of electron density over there. Yeah. That make?
Yeah.
Okay. So this one here, this is the SN2 step. And in this case, we're doing the nucleophile with the substrate, right? Or another way of saying that is the electrophile. And again, we're going to have that same sort of lineup, aren't we? So which side does that have to line up on? with the carbon, doesn't it? Okay. And so this lineup needs to look something like that. So our HOMO, again, needs to be able to come in here and overlap, have a good overlap with that LUMO on the carbon, right? Which is going to be your lowest energy unoccupied molecular orbital. Do you remember where I was talking about electrophiles and how good of an electrophile they are? This is why you need those orbitals to be able to go in and reach things. Is you actually need this overlap to occur to have the electrons flow into that bond, right? If we had a really small orbital, would that be able to overlap right here? No, there's hydrogens there, aren't there? There's stuff blocking it. So it can't just get right up next to the carbon to overlap, can it? Okay? And that's actually why you have issues bonding things with really small orbitals or really, really compact, like fluoride. Miserable electrophile. Real small orbitals. Okay? Okay. So here we have a forbidden overlap. That's the reaction's not going to occur, right? Okay. Remember how we said the stereochemistry inverts whenever we do this overlap? We're going to always attack from the other side. It'll invert the stereochemistry. This right here is why. You can't attack from this side, can you? You can't overlap the orbitals. And so any attacks from this area right here is not going to give you a meaningful collision and not going to give you a reaction, is it? It's only when we attack from the opposite side of the leaving group that we can get a meaningful reaction. Okay, so let's go and look at the bond formation, which is the coordination reactions, or the bond breaking, which is the heterolysis reactions. So here again, it doesn't really matter if it's a Lewis base or nucleophile. The other one's going to be a Lewis acid or electrophile. Again, it doesn't really matter. We're going to have the electrons going into the bond. And again, the Br minus is going to be that relatively electron rich. And so that one's donating the what orbital? The HOMO, right? Okay. This other one is electron poor, and so that's donating what orbital? Yeah, your LUMO. Got it. Okay, now when we look at the overlaps here, this one actually has more options for the overlap because it has that p orbital that will be above and below. Remember that? Okay. Can everybody see that kind of? That's trigonal planar. There's three things around it. So you're going to have a p orbital above and below it that are empty. Okay. This would be a degenerate orbital that you can fill in, okay? Okay, and so what you're going to get is you have a proper overlap if you take the HOMO and LUMO from this direction, but you can also do it from the other side because, again, they're both empty. You don't have electrons in them. It's just that positive charge on the carbon there. Okay. Everybody see that okay? Okay, and that's that empty p orbital. All right, so let's look at the heterolysis step. Here we have the leaving group leaving, as it were. Here we have the iodide taking that electron density. So again, the heterolysis is the reverse of the coordination. So you could look at it as a heterolysis, but you could also just take the microscopic reversibility and then look at it the reverse direction. That same orbital overlap, those same energetics have to apply in both directions. Okay? Yeah. And so that's what that equilibrium arrow, by the way, means. That we can look at this in both directions, right? Okay. This is right here is going to be your nucleophilic addition and nucleophilic elimination steps. And so this one's the addition here. And so we're going to have that partial positive charge on your carbon here, which is your electrophile. Your nucleophile is going to have the orbital with the electrons overlapping that unoccupied molecular orbital, right? Okay, and so we go ahead and look at it in terms of orbitals. And what we can see here is that there's actually two directions for this attack. And the reason for that is because we actually have orbitals this way and orbitals this way that both are going to be lacking electron density, right? They're not going to have electrons in them. They're going to be your unoccupied, lowest unoccupied molecular orbitals. In this case right here, we're going to have the electrons going up on here, right? Okay. And so, again, the LUMO is actually the pi anti-bonding orbital from the CO bond here. That's actually what those orbitals are. Okay. That's actually why the electrons then flow up onto the oxygen, is because those are the ones that the electrons go onto. The pi bonding then ends up having the electrons flow up onto the oxygen because they're being shunted from their anti-bonding here. All right. Okay. Let's look at nucleophilic elimination. So if we look at the nucleophilic elimination, it's going to be that same combination of orbitals and the same energetics. This is going to mean that we can actually look at it from either direction, right? So we can look at this same diagram and go, okay, we have the electrons up here. This can then flow back down, and one of these can leave then. If we get an overall reaction, that meant this one left, right? So the electrons actually flowed down into here. Right. Which is what we're seeing here. And again, we can look at it from either direction in these cases. Okay, so let's look at the bimolecular elimination. Again, this would be your E2 steps. This is going to be the formation of two separate bonds and the breaking of another two bonds. Now, in this case, because we have the multiple bonds, it can get a little bit complicated if we look at everything at once. So to simplify, using the FMO theory, we're going to treat that entire process as two separate parts, even though it happens all in one go, okay? We can do something a bit like a resonance structure, right? To look at what it looks like overall. Okay? We're going to treat this as one OH bond and breaking the HC bond, which is this part right here. And then we're going to treat it for the second part as the pi bond forms, and then we break the CBr bond. That's this part right here. Okay? And that's going to allow us to look at these as individual structures we can deal with more easily. All right, so let's look at the HC bond coming apart, the hydrogen acting as a Lewis acid, as it were. That's this one right here. Did you notice it looks a lot like the other one that we looked at before? Yeah. Again, it's going to be the LUMO on this hydrogen here, right? Overlapping with the HOMO on this OH. That is then going to give our intermediate structure. In that intermediate structure, we'll have negative charge starting to build up on this carbon, right? Okay, by the way, that is a sigma star or sigma asterisk. It's the anti-bonding sigma orbital right here. Okay? Everybody caught on to that, right? That these are always your anti-bonding orbitals? Mm-hmm. Yeah. Yeah, the lowest energy unoccupied molecular orbitals are essentially always your anti-bonding orbitals, unless you have something like the carbocation. That one would have a bonding orbital that would be free. Okay? So these ones are always your anti-bonding orbitals. Those are the ones that would be without stuff in them. Okay, and so the next part is going to be where we have this this hydrogen right here on the carbon. And so what we see here is the HOMO and LUMOS. The HOMO is going to be this hydrogen here. And the LUMO is going to be this one right here. Okay? And that one is that anti-bonding. This is the anti-conformation, by the way, for making the anti-conformation double bond. If we have an overlap with this LUMO here, this is going to be a direct overlap with this HOMO and this LUMO here. Now, that will give us the anti-conformation. Right here, the HOMO and LUMO do have a substantial overlap, but what do we notice about this overlap? Is it as substantial as over here? Okay. So this is the overlap in electron transfer that would have to happen if we were to get the syn conformation, these on the same side. Okay. And so which overlap do you think is more likely? Yeah, the anti, right? We have a better overlap. Okay. And so the fastest forming one, the one that's going to form the most, is going to be the anti one, right? Okay. And again, this is because you have a much better contact, a much better overlap, right? In this one here, we have significantly less overlap because it's the other side, that smaller lobe of that bonding orbital, isn't it? Okay. All right, so let's look at the electrophilic addition here. Again, remember that each time we do these, electrophilic addition is just going to be the same but reverse for electrophilic elimination, right? So we don't have to think of these things as two different reactions. In terms of the frontier orbitals, they're the same thing. Okay, so here we have a double bond. This is going to be our electron rich. Here we have the electron poor hydrogen. And so which one has the HOMO LUMO again?
The carbon is HOMO, hydrogen is sigma.
Yep, you got it. The double bond is the highest occupied molecular orbital. Very good. And so this is what that looks like. So here we have the double bond. Notice it has both sides, above and below. They say it okay. And then your hydrogen is going to have its orbital overlap. Note that it is attacking basically from the center, isn't it? How do you end up determining which side it ends up on?
Anti or
There's no difference in overlap, is there? See that? We don't have any real difference in overlap, do we? Yeah, because those pi bonds keep everything away from them, don't they? They force everything to be planar. And so what ends up happening is which one it ends up on is entirely determined by the stability of the carbocation. Yeah. That's it. So whatever can support the stability of that carbocation better, that's the one that ends up being the preferred conformer. Okay. Okay. And again, there's no speed difference in the overlap. So this overlap, which side it attacks faster, that ends up not being a concern for these ones. Okay. This is the HCl anti-bonding sigma orbital here, by the way. And this is, again, the pi orbital in this case. Notice there's a lot of similarities between the electrophilic. And if we were to look at the other one, the eliminations, we have a very different combination here. But if we look at these, they're actually quite similar, aren't they? It's just in terms of pi bonds. Okay? Okay. All right, so again, remember that you're always going to be, the HOMO is what again? Highest occupied molecular orbital. That means it's going to be the one with the electrons in it. That means it's the one that's a bonding orbital typically, right? The LUMO is going to be the highest, the lowest unoccupied molecular orbital, unless you have extra electrons or less electrons on something, like a carbocation. That's always going to be an anti-bonding one, right? Okay. Okay. These, when you start looking at these, you can see a major pattern whenever you're thinking about these. That if you're dealing with a pi bond in some way, right, then you're going to involve a pi orbital, aren't you? Okay. If you're dealing with single bonds, you're going to end up involving sigma orbitals, aren't you? Okay. And this is how you can help yourself keep track. If you go here and you're like, okay, I gotta attack that bond somehow, my electrons are in that double bond, right? If you can get that far, then you can actually predict the rest. The electrons are in the double bond, that means they have to be in the pi orbital, okay? And that has to be a bonding orbital, doesn't it? And that means that is the highest occupied molecular orbital, right? Okay. On the other hand, the other one only has a single bond. That has to be a sigma orbital, doesn't it? It's neutral, and so it has to be the lowest unoccupied molecular orbital, and that means it has to be a sigma orbital that's an anti-bonding sigma orbital. Okay? Can everybody see how you can work through these? Okay. You only need to remember parts of it to get everything else. It's all logical streams, one after another. Okay? All right, so the electrophile elimination steps. Again, we're going to be having this H2O here. That's going to be your source of electron density. Notice it's going to be attacking this hydrogen again. This is going to be the electrophile elimination. It's going to be the reverse of the electrophilic addition. So we're going to be having the same thing in reverse. Again, this has to be the same because of that principle of microscopic reversibility. And it has to have the same allowed step. So we can break this into sort of two parts here. Right here we have this oxygen taking on the hydrogen, right? Giving its electron density into that. Over here we're going to have this p orbital, right? Remember that p orbital that has doesn't have anything in it, and this positive carbon. So this is going to take that hydrogen, leaving you at the double bond. That's going to end up being a pi orbital, right? Okay, let's look at the orbitals here. So when we have this is the hydride shift, and that's what that would look like, right? So when we have this hydride shift, remember everybody how I was talking about how the orbitals have to overlap and it's pulling electron density from that hydrogen bond orbital? That's actually what we were talking about. We'd always been talking about a frontier molecular orbital theory. It's just we hadn't covered it yet, so we couldn't go into depth. And so what you're having here is the bonding orbital here, which is, again, a HOMO, right? This is going to overlap with the LUMO. Interestingly enough, this is actually the HOMO and LUMO on the same molecule, which is pretty funny, right? I know, right? We're actually having the HOMO and LUMO on the same molecule overlapping. And so it's going to pull the electron density over. If this gives you a lower energy overall state for that filled orbital, for that highest occupied molecular orbital, that's going to be the preferred one. And the reaction will go forward. We'll have a hydride shift. Okay? And those things that we talked about before, whichever one has the more substituted carbon to share that charge, those are still true. Okay? We're just looking at them now in terms of molecular orbital energies. Okay, that's actually the end of that. We'll go on to some more naming. Everybody excited to go on naming? Okay. No?